Hello, good morning, everybody. Okay, so we are going to start our lesson soon. So let's wait for another 1 or 2 more minutes for your friends to arrive. And I think today we can finish the syllabus for this one, D block element, and we are going to finish for the semester 2. And you are going to start to do your practices already. And then beginning next week, we will discuss the practices for semester 2. Okay, so without hesitation, shall we begin? Okay, so we are going to start off with the from where we stopped yesterday. So yesterday we stopped at why is transition metals colorful. So I hope that you have already highlighted the key points that I mentioned yesterday, and then you'll be able to explain why is a transition metal colorful. Okay, so let's go to the last chemical properties of a transition element is where catalysis in the D block element. Okay, so the catalysis in the D block elements. Okay, what is actually a catalyst? So a catalyst is defined as the substance that increase the rate of reaction without changing its chemical composition. How does it do it? It do it by lowering the activation energy. Okay, so by lowering the activation energy of the chemical reaction and by providing an alternative route or alternative reactions pathway. Okay, so a catalyst may react to form an intermediate. So what is an intermediate? As I already explained during semester 1 last time, intermediate is a species that is appear during a chemical reaction but will not form as a product. Okay, so now in here, during a catalyst is applied, the catalyst may change its structure or form. Okay, even physical properties may change. Okay, but at the end of the day, it will not form as a product. Okay, so transition metal is usually a good catalyst. Why is it a good catalyst? It is due to the availability of the MTD orbital and also the ability to change its oxidation states. So this, because of these combinations of these two factors, it makes transition metals good catalyst. Okay, so catalyst reactions is specific and different. Transition metal has different effects towards the rate of reaction. So that means that only certain reaction is catalyzed by that specific catalyst. Okay, so you cannot simply add any transition metal then claim that it is a catalyst. No. Okay, some of the examples of catalysts are shown below. Titanium is used as TiCl4. I think I already corrected in the notes. TiCl4. This is also known as the Ziegler-Natta catalyst. It is used in the polymerization process of the polyethylene. As you already know during your SPM last time, vanadium oxide V2O5 is used in contact process to catalyze the reaction from SO2 to become SO3. Iron is added to this Haber process, a process to synthesis ammonia. And then nickel is used for hydrogenation of the unsaturated hydrocarbon. Okay, and last but not least, platinum is used in the Oswald process, the process of manufacturing nitric acid by first forming the nitrogen monoxide in here. So these are the few examples of the catalyst that is used in our industries nowadays. Okay, so catalysts can be generally divided, as already learned during our semester 1 last time, we already learned that catalysts can be divided into two types. One is a homogeneous catalyst, another one is heterogeneous catalyst. So what is the differences between a homogeneous catalyst and a heterogeneous catalyst? Let's have a look together. In homogeneous catalyst, we say that reactant and catalyst are dispersed in the single phase. That means they are in the same state of matter. Okay. So acid-base catalysts are the most common type of the homogeneous catalyst in the liquid reaction, and there may be some process which involve a redox reaction using transition metal as the catalyst. So this is one of the most common example of a homogeneous catalyst. Try your best to remember, which is the reaction between the disulfide ion S2O8 2- and iodide ion I-. So it can be expressed by the following reaction where we have S2O8 2- plus 2I- give I2 plus 2SO4 2-. Okay, now this is a one-step reaction that can occur, but it occurs very slowly. Okay, without the catalyst, it occurs very slowly without the catalyst. Okay, so this spontaneous reaction is a single step reaction and takes a very long time for the reaction to complete. So because the activation energy to reduce the S2O8 2 minus is very high, so that is why by adding iron 3 sulfate, or by adding anything with iron 3 iron 3 nitrate or whatsoever. Now it depends. Sometimes they say add iron 2, sometimes they say add iron 3, so it depends. Okay, so by adding iron 3 sulfates, the steps reaction is altered as described below. Okay, so how does the steps alter? So the first step is your iron 3 ion is act as an oxidizing agent, okay, catalyzed by the reactions by acting as an oxidizing agent, which oxidize the I minus to become I2 first. Now this can be deduced by the spontaneity of a chemical reaction. If you have the E naught value with you, so what are the two E naught value? We shall first have I2, sorry, 2I minus give I2 plus 2E minus. So this one E naught is equals to negative 0.54 volt. Okay, and then you have a Fe3 plus E minus give Fe2 plus. Okay, so E naught is equals to positive 0.77. Okay, so as a result, the overall equation, so you shall have 2 Fe3 plus 2I minus give 2 Fe2 plus I2. So E naught is equals to positive 0.23 volt. Okay, so now throughout the process, you form Fe2 plus. Then this reaction is further used as an reducing agent, okay, where the Fe2 plus will react with the disulfate ion accordingly. So this can also be deduced in the equations, where you have Fe2 plus give Fe3 plus E minus. E naught is equals to negative 0.77. And then you have S2O8 2 minus plus 2E minus give 2SO4 2 minus. This one E naught is equals to positive 2.01. So as a result, you shall have S2O8 2 minus plus 2Fe2 plus give 2Fe3 plus 2SO4 2 minus. So the E cell is equals to positive 1.34. So the positive E naught values 1.24, sorry, 1.24. 1.24. So the positive E naught values is trying to tell you that the reaction is spontaneous. Okay, so that is how you are going to prove that the spontaneity of a chemical reaction for catalyzed reactions in here. Okay, so it helps to it helps to speed up the reaction by providing alternative routes which require lower activation energy. Okay, so and if you see carefully, Fe2 plus is formed temporarily during the reaction. That's why we say Fe2 plus is the intermediate of the reactions. Okay. Okay, so I'm going to print screen. Okay, so this is the energy profile for the reaction. Now, if you still remember, when we discussed about the energy profile, we say that one step, one loop for one single step, two loop for two steps in here. Okay, so the green line color is the uncatalyzed reactions. Okay, so this is the uncatalyzed reaction. Okay, and then this is the catalyzed reaction. Okay, and then this one is EA. Okay, so that is what is going on. Okay, so that is how you are going to express the energy profile for the reactions in here. Okay, so with that, that is for the homogeneous catalyst. So what is a homogeneous catalyst? A homogeneous catalyst is a catalyst where the reactant and the catalyst are in the same state of matter. Okay, so the other type of catalysis is what we call as a heterogeneous catalyst. So in heterogeneous catalyst, it is the reactant and the catalyst are in different phase or in different state of matter. Okay, so usually in most of our case, catalyst is a solid, while the reactant are either a gas or a liquid. So one of the examples is the reaction of the hydrogen towards the unsaturated C double bond C in organic compound to form a C single bond C. So it has been used a lot in petroleum, plastic, and food industry. So examples is the conversion of vegetable oils into margarines, okay, where according to the equation C2H2, CH2 double bond CH2 plus H2 give nickel under 200 degrees Celsius to form ethene, CH3CH3. So this reaction uses nickel as a catalyst, and the two reactants in here are gases. So that is why we say that it is a heterogeneous catalyst. Okay. So in heterogeneous catalyst, these are all towards explanation. No equations. So in heterogeneous catalyst, reactant normally occur on the surface of the catalyst through absorption process. This is a very important keyword. The reaction occur at the surface of the catalyst through adsorption process. So what is the adsorption? Adsorption is physically absorb the reactants. Okay, so by how transition metal have certain active site at which the reactants may adsorb. So when the adsorptions occur through the formations of the covalent bond, okay, so such absorption is also known as chemisorption because you form a chemical bond throughout the process. But and this is able to do because of the empty d orbital to accept the electron. Okay, this is able because the empty d orbitals enable it to accept the electron pair, especially from the pi bond to form a weak bond. So when there is a weak bond established between the surface of the catalyst and the reactants, okay, so it will weaken the bonds inside the molecule. So new bonds start to form, binding the reactant gas, thus forming the product. And at this process, the activation energy is lowered because catalysts provide a surface for the reactant to come close to each other that favors to the reactions in here. So if I explain just like this, maybe you won't be able to understand. Why don't I show you through a diagram that how does the catalysis in here take place? Okay, so in here, as you can see from the diagram, this is the surface of the catalyst, which contain active site. Okay. And you're able to form the covalent bond by using the empty d orbital. So such process of this catalyst absorbed temporarily to the surface, we call it as a chemisorption in here. Okay. Okay. Then as this happens, the hydrogen bond in here is weakened. And broken. And the hydrogen will attach to itself to the pi electrons inside this one. Okay, so when you start to form the C2H5 already, then the molecule, the hydrogen left, okay, the hydrogen left in here, okay, will go and find the C2H5 and attach to the other side, and hence release to form the C2H6. Now, because this one, the bond between the surface and this one are very weak, so it can come off very easily, okay? So these are the important keywords that you need to highlight whenever you are trying to explain a heterogeneous catalyst in its actions, okay? Okay, so with that, that is for the explanation of a homogeneous catalyst and also heterogeneous catalysis in here. Okay. So hopefully you all can understand better. If you cannot later, I will send this video to you, and then you can re-listen again if you cannot understand, or you can always Google in the Google to understand more about the process. Maybe there is animations, I don't know. Okay, so you can try your best. Okay. So with that, that is for catalysis in the transition element. Okay, so there you have the 4 chemical properties of the transition element. Number 1. Transition element can exhibit multiple oxidation states, okay? And then number 2, transition metals can form complex ion, okay, complexes or coordination compound. And then the third one is the transition elements, transition metals compounds are colorful, and finally transition metal act as a catalyst. So these are the 4 common chemical properties possessed by the D block element. We have already gone through one by one, and you try your best to remember as much as you can. Okay. Okay. So for the final part of our lesson today, we are going to learn a little bit about the uses of the D block element and their compound. So titanium is one of the most abundant metals on Earth. So it exists as a rutile. Okay, the ore is a rutile. And it has a lot of properties similar to that of aluminium. For example, high tensile strength, get brittle, it is light, it forms protective oxide layer when exposed to the air. Okay, and titanium are extracted from its ore using Crow process, which contain 3 stages. So the first stage is the titanium oxide is added to the H2SO4. So this is acid-base reactions. As you can see in here, sulfuric acid acts as a Bronsted lauric acid. Okay, so you form TiO2 plus SO4, and then the titanium oxide then is further dissolved in the water to form a white precipitate. Okay, so this is hydrolysis. Hydrolysis, so you form TiOH4, and then the white precipitate is filtered, then it's heated strongly to become TiO2. So now this is how you get the impure TiO2 from its ore to get the pure TiO2. Okay, then the next step is the extraction of the this one. So when the pure titanium 4 oxide is obtained, it is then heated with chlorine under coke to form TiCl4. Okay, where TiO2 plus C plus 2Cl give TiCl4 plus CO2. But this TiCl4 is very hygroscopic. That means it can react easily in air. It is very similar to like that of SiCl4, where if exposed to water, to vapor, it will form back TiO2 plus 4HCl. So therefore, to prevent this to happen, so chloride is stored in the bronze container containing argon gas. And finally, the titanium 4 chloride is then reduced by using magnesium to form the pure titanium. Okay. So what are the uses of titanium? Since it is light and have a protective oxide layer, it is also used together as the alloy for aircraft and jet engine. It is also a reactive to non-metal gas and therefore form alloy with iron to remove the combined oxygen and nitrogen. And then titanium oxide is often used in the pigment of the paint, especially for the white color paint. Okay, so that is for titanium. And then the next one is chromium. So bright shiny metals which form a transparent stable oxide layer on its surface. So this is useful to iron coating to prevent the corrosion of iron. This is also known as the stainless steel. So chromium in the stainless steel is the one that makes it become stainless. Okay. So important ore of the chromium is chromite, which is made of FeOCl2O3, which are found 95% in South Africa. And then the chromium oxide is then reduced by using aluminium through thermite process. So this is how you get the pure chromium out from it. And then the pure chromium obtained is then electroplated to protect the surface of the more reactive metals such as iron. So it is used to form a ferrochrome alloy in the making of the steel. And then concentrate chrome is then reduced by the carbon. Okay, so this is a mixture of the ferrochrome alloy contain iron and also chromium, which is used to make heat-resistant alloy and also stainless steel. Okay. Okay, so uses of chromium, as we mentioned just now, added to steel to harden the metal and also to electroplate. Chrome alum is used in the printer ink. It is also used as an oxidizing agent in the form of like chromate Cl2O7 2- used in laboratory, and it is especially important to make stainless steel. It is heat resistant and do not rust easily. It is often used in kitchen utensils like cooking pot, fork, spoon, gates, and fences. Okay. Okay, then we go next to the cobalt. So cobalt is primarily used as a metal in the preparation of magnetic, wear-resistant, and high-strength alloy. So the most important oxidation state of cobalt are +2 and +3. So cobalt +2 is blue in color. So try your best to remember. Cobalt +2 is blue in color, and this blue in color is often added to the gemstone. Is often used to make the gemstones because of its attractive blue sapphire color. And it is also added to glass to give the blue color of glass. It is added together with aluminium to form the blue pigment in the paint. Okay, so these are these are usage of cobalt, nothing much really. And last but not least, manganese. So elemental manganese is hard and shiny like vanadium and chromium. It is used to make the steel alloy. So a small amount of manganese makes steel easier to roll, forge, and weld. Steel made with 12% of the manganese is tough enough to use for naval armor. That means the anti-bullet armor and also anti-missile armor. Front end load bucket, okay, and other extremely hard object. Okay, small amount of the manganese are added to the aluminum beverage, and the bronze alloy makes them safer and tougher as well. So manganese does not exist free in nature. That means you do not have pure manganese. So main ore of the manganese is pyrolusite MnO2, which is a black solid. So manganese oxide is insoluble in water, dilute to acid and alkali. Steel magnesium oxide is amphoteric as it can react with concentrated acid and concentrated alkali. It is also a strong oxidizing agent. Okay, so some of the uses of the manganese include pyrolusite is used to make ferromanganese alloy together with the iron. It also used to decolorize the glass. It forms a brown glaze on the pottery. And the crunchy cell. What is a recrunchy cell? Recrunchy cell is your normal dry battery. Okay, the battery here. We call them as a crunchy cell. Okay, where hydrogen produced around the cathode. And last but not least, KMnO4 is also used as an oxidizing agent. Okay, so with that, we finish chapter 7. Okay, so finishing this chapter means that you have to start doing your practices already. So try your best to do the practices. And then beginning next week, we shall discuss the questions inside the books. Try your best to do all the exercise inside the books. So I guess that is all for our classes today. So have a great weekend, and then I'll see you all on next week. Okay. Okay. So thank you very much.
Thank you, teacher.
You're welcome.
Thank you, Mr.
Teacher.
Welcome.